Hi everyone, this is just another short video to try and show some basic functionality of how we can create frame element models or models with wire parts where we then connect things together using a connector assignment, or in this case we're just going to use a hinge. So I haven't got a specific model in mind that will flash on the screen. I think we can have a look at this type of bridge structure maybe again that we did in class, where we have an infill span. So getting to it, I'm just going to create a part we can call left span maybe. It's a 2D planar part, wire feature. In total this bridge length will be about 40 meters maybe. So I'm going to start here at the leftmost edge or the left support at 0,0. We first select our wire or line there. We start at 0,0 and I'm going to go to the right, say about 10 meters, 0,0 up to the first support. Then we're going to have a little overhang end here that might be about 2 meters, say. And that put us at 12,0. And that's our first part of the model that we're going to define. I'm just going to cancel that procedure and then say done. The reason I defined one part for this is that at the rightmost end here we will have a hinge. Basically we need to define a second part for that infill span. Now this type of model could be modeled symmetrically if the loading is symmetrical. In this case I'm actually going to make the loading unsymmetrical. So we actually have to then duplicate this left span with its overhang end to be a right span with it. So we could draw the new model, or we could just say, if we click on part, left span, we can make a copy. It asks you what you want to name it. We're going to call it right span. And we can mirror it about the YZ plane, right? So YZ coming out of the screen here, that's where we mirror it. And we can say, okay, well, it won't look any different. But basically, we've got two parts there now at the moment. Next thing we want to do is create the final little infill bit. Now for that, again, just a straight line. I'm going to call that infill or infill span. And again, now here we need to just decide how long that infill span is. I'm just going to start at 0,0. You'll note that I don't even start at the correct coordinate in the sketch space, because eventually I'm going to translate the part. But let's say that infill span is about 5 meters, or exactly 5,0. There we go, done. So that's part's been created. There's quite a few things we need to assign now. I'll start with the material. I'm just going to use the basic stuff here. Elastic material, steel I call it. Young's modulus of 200 gigapascals, Poisson's ratio of 0.3. And then what I'm also going to add this time around is the actual density, so we can add a gravity load case. 7850 kilograms per cubic meter. We define the steel. Now for the profile, we can obviously do a section for the back spans, for example, or the left and right spans. And then I'm just going to say, let's make that rectangular shape. And it's, we can choose anything here really. I'm just going to say, for example, that A is 1 meter and B is 0,3 meters. It's quite a wideish concrete section. Right, so then we create our sections. We're going to do beam sections in all cases. So I'll just leave the name as section 1. We continue there. It's got our profile for the back span. And it's a steel material. So that's great. We actually have, let's do another section or another profile for the infill span. We'll call that infill, again rectangular, but just for argument's sake we'll keep it a meter wide, but we'll make it 0.15, half the depth of the previous section. Then we can just create another section here for the infill. Maybe I should call it infill just to be clear what we're looking at. And again, that we now have to select infill there for the profile, and there we go. Now we just have to assign these things to our parts. So for the section assignment for the infill span, we select the whole thing there and we say that we're going to have the infill section. And then for the left span, we can do a section assignment again. Sorry, just take note, you have to select that short little bit at the end as well. And we're going to call this, I should have changed the name maybe, but section 1. Right, and then the last one is the right span. Again, section assignment. We can create or select the whole set. You'll see there again, this overhang end is separate. So we say done there. And it's again section 1. We also have to assign beam orientation, so we can go here by assign beam orientation. We're now busy with the right span. We select that, it shows us the tangent vector, and now you'll see that the actual 2-axis of the section is pointing downwards. To make it point upwards, we can go and say, first assign the tangent vector, so it asks you select the edges whose tangents are flipped. So you can just say, okay, the whole thing you want it to be flipped, and it will go the other way. Then you can, sorry, let's just say done there, and then you can go, I'll press that button, get back to orientation. We select the whole right span, and it shows us that the 2-axis is now pointing upwards. I mean, in the final answer, it won't make any difference really. It's just clearly when you've got a monosymmetric beam or a T-beam, for example, then you want your top flange to be at the top of the section. So then you have to get the orientation right. Right, for the left span, we're going to do the same. Just go to that part, and we select our section there, and let's see the tangent vector in this case should be correct. So 2-axis pointing upwards. Then for the infill span, last one up, we can do the same thing. It seems to be correct for the tangent direction, and 2-axis is pointing upwards. We've done all that, so we can also mesh this now. I'm just going to say, okay, let's go to the meshing module for the infill span to start with. You can just select the element type here. Beam, cubic formulation. Let's leave it at the shear flexible formulation. And we're going to assign, using the seeding of edges, not the global seed. You can actually select that and say we want in that span, say 10 elements. Now there's an interesting thing that you could actually do if the problem doesn't really warrant it, but you could actually have a bias in your appointment of elements so that you can grade the mesh from large to small. Have a look at that when you're playing around with Abaqus. Just going to apply that, and I'm actually going to mesh the problem, or mesh the infill span. Same thing for the left span. Our selection of elements should now be correct here. You just check that element type will still be set. It asks you for the regions, we select those regions, and you can see it's still on shear flexible there, so we're okay. I'm going to assign a global seed to this one. Why not? Let's just do that. Give us okay grading there. Maybe not too many elements on this side, or not enough. So what I'll do there is can even go and say you want to apply a local seed to that part of the number of elements there. Let's put it up to 4. Okay. Now this is just a demonstration, it doesn't really matter, but we'll keep it consistent with the right inside. So the right side, we're going to go mesh, We're going to seed first the global seed, approximate global size of 1, we apply that. We do the local seed on this side of the element, or on the part, and we can again do 4. Okay, there we go. If we mesh that, it should now be meshed. Right, so we've done everything to create the parts. In the assembly step, we can now go and say, instances. We're going to go and say create instances. Now there's 3 parts. We can do all 3 in one go. Select all 3 with shift select. And just remember to tell it to auto offset from other instances, right? So, okay, there we go. You'll see the arrangement is wrong. Just take note that I'm not sure that we meshed this one. And also it helps if you go view, assembly display options, mesh, and then in all assembly related modules we will show node level. Okay, so clearly I forgot to mesh this one. We'll just go back to that left span, and the seeds have been assigned, but let's just mesh that. Should be fine now. Back to the assembly. It shows us our 3 parts there. Now clearly we want to move them into the correct position, so first off we can just translate parts by clicking on translate instance. So we're going to select that instance for the first one, and we can just translate the part out of the way maybe. We haven't got a reference point for that, so we'll just select that point on the left there. Okay, now those 2 parts are overlaid, so if we select the next one, hope it's going to do it for us. We're going to translate the infill span. So there's actually 2 things it's selecting there. It's a bit difficult to translate it that way. You can click on instances, obviously. Infill span, sorry for that little hiccup. And then we're going to go left node there. We're going to translate it to that point. Fine. Okay, last one to translate is this instance on the right. And we're going to say that instance is selected are done. And we start at this node and we end that node. So we've joined our bridge structure together like this. The meshing seems fine, everything seems fine. We're just going to create a load step quick, call it load. Defaults are fine there. I'm going to later on want to plot the moment diagram, so I'll again go field output. I'm not really interested in the stresses and the strains for this model. So I'll take those out, but I'll add this node force in the beam section orientation. Right, so we've created our field output that we're interested in. And then I'm going to assign boundary conditions, displacement rotation conditions to start with. So we're just going to have pin supports, obviously now, these locations, not at the end of that little mesh bit. Right, so there, and over there, and right at the far right end of it. If those are correct, so we can say done. Pin supports. Obviously we could add a roller to the end of the beam here. It's typical on bridge structures, but I'm not going to do it just to save some time here. Right, now we've got boundary conditions, but we haven't actually connected our infill span yet. So to do that, we first have to go and say, let's create a connector section, for example. And I'm just going to, well, we can call it hinge. The type is a basic type. We're going to join the translational degrees of freedom. rotational degrees of freedom are the ones we want to actually go specify that UR3 is free. So if I continue that, you'll see another little menu popping up that you have to actually now specify the behavior of the section, sort of like we've specified the elastic properties of the material. So we say a plus there. Then we're going to specify some elastic behavior. You'll see that here you can now actually, if you select M3, that's the rotational moment, you could actually give it a spring stiffness, D66 there, if you want to handle it like a spring. Otherwise, we can go rigid and say, if it's fully rigid, then rotations about the x-axis, rotations about the y-axis are fixed, but we leave rotations about the z-axis free, which is what we want at that hinge. We've created the connector section. You'll see here, if I go back to the sort of toolbar, you can also then assign connector sections in this with this tool. But to do that, if you click on it, it's going to ask you for a wire or attachment line. Now, like I've said in class, in Abaqus, you can actually have connectors that the 2 points you are connecting aren't coincident. So what you want to do first is escape that thing and go and create your wire feature. So what we're going to do, we're going to have disjoint wires, otherwise it's going to chain it, and we're going to select 2 points. Now you want to be here at the end of the left span with its overhang end. I've selected the first point. The second point is on top of the first point. If I say done, it'll show us left span 1 vertex 2, infill span 1 vertex 0, so that's what we want. We can add another one and say, right, so over here, going to be again, choose those 2 points that lie on top of each other. Right span 1 vertex 2, infill span 1 vertex 1. Right, and then just make sure that you can create a set, otherwise it doesn't really matter. Okay, now when we go back to this toolbar and we say create connector assignment, it says assign now, or choose the wires where you have these connectors. So I'll choose both of those definitions we've made. Say done. And the connector, we've already created that. We call it a hinge. Hopefully that's all going to work fine. Last thing to do is to just actually apply load. Now, I'm going to apply some non-symmetrical loading to this thing. We'll use our global axis system to define an analytical field again. But obviously you can create a local axis system at the center of the span, to define different types of loading. First, to use an analytical field, we just have to go and create our analytical field. So we're going to say it's an expression field. And I mean, you now obviously have to work out what you want to give it here. So let's say it's a sort of triangular distribution. And it'll increase as we go towards the right end of the bridge. So in this case now, you could then just say, if you have to work out the slope of the line, it will obviously be the load over the x distance. I'm just going to give it a value here now. So let's say that's 10,000 or 10 kilonewtons per meter times x, where x is obviously our distance in meters. I'm not actually interested in what the final value comes out to in this case. Right, I've defined it now as a positive analytical field. So when we actually define the load, we have to go and say, we'll do that first load, we'll call it a line load, and we'll do that in the load step. And then we're going to choose, let's say, our whole assembly. It's in the global axis, but we're actually going to do analytical field 1. And then because it's in the global axis system, it asks us for 2 values here. You could also go local, then it's local to the beam element. So our 2 axes were always pointing upwards in the beam element. So if we go local, it only gives us component 2, in other words, perpendicular to the beam. If we go global, you can actually have 2 values to that analytical field. Let's say local, and obviously now we have to go -1. It's multiplying basically our analytical field with -1. Right, so if we do that, you'll see that it only shows little squares as the load gets bigger from the very left end of the bridge. If we go back to our load definition, you can actually then now switch on here that you want to see it in the global coordinate system. You'll see there's no component Y there now. And it does show us the correct triangular distribution. So the two things are equivalent, obviously, because the global and local coordinate systems coincide in this case. Other thing we need to do is add our gravity load. So I'm just going to create another load and we're going to call it gravity. The distribution is uniform. The whole model has the gravity assigned to it. And again, this is in the global coordinate system. So we want to say in the Y direction we have 9.81. Just take account of your units. I'm using meters here, which is consistent then with the acceleration of 9.81. Okay, so it does actually now show us a big arrow there for gravity loading, but it just shows that arrow at the sort of global origin. Right, so that's the whole thing as far as I know. It's always tricky when you press, let's call this example, and we create that job. Sorry, I just need to save this still. We'll save this as my temp folder and my C drive just as an example. Hinges, so I can get it back later on. There we go. I never know if I press run whether it will actually do it, but I'm fairly confident, so let's see what happens. It's done. Wonderful results. Starts off showing us nothing, then it shows us the deflected shape. Normally it would show us 1 meter stress, but because I switched that off, it's not available here anymore. So it defaults to concentrate force, the next one up. We obviously just say want to see deformation. Yeah, seeing quite a strange deformation because of that triangular load, but I think the more important thing we want to see is the actual moment diagram. So again, you can go here to contour options, and I'll show tick mark labels. We say OK, and again, if it's in the deformed coordinate system, the moments are difficult to read, so just go to the undeformed shape. What's important is right here where we have that last node, we've got 0 moment. That's exactly what you're expecting. And also on the triangular load where we've got the big portion of the load, it's on this right span, you get the bigger deflection. Sometimes a vector plot is more informative if we go for the vertical deflection, for example. Again, the undeformed shape helps with it. What's interesting, obviously, from this is that because of the large load on the right span here, we're actually getting an upwards deflection on a portion of our deck over there on the other side of the support, sort of this overhang end. Right, so that's the basic sort of functionality in terms of putting in hinges, and again showing how to do analytical loading. There's obviously a lot of interesting things you can do with the output. I need to emphasize though that because this course is called Theory of Structures, I want to ask that you do not get a hang up on just being able to use Abaqus. A large portion of the marks in any of these questions are actually assigned to using the data to do something. Calculate the maximum stress in a beam, determine the position of the maximum bending moment, and then that's why you need to be able to then actually use your output to do that, and then basically maybe go and calculate some other quantity that's important for the engineering design. For example, if we were to change this to a concrete material, obviously it ties in nicely with what you're doing at the moment on the design of concrete structures. So that concludes the video. I hope you find it informative.